In this video, we are going to study some of the properties of the transition elements, and we will do that by focusing mostly on the first series, which is the 3D series. So let's begin with the physical properties. We know that transition elements have metallic properties. They have high tensile strength, they conduct heat and electricity, they have metallic luster, and are also malleable and ductile, which are the characteristic features of metals. With a couple of exceptions like zinc, cadmium, mercury, and manganese, all of them have metallic lattice structures. Transition metals are also quite hard and have high melting and boiling points. And this high melting point is due to the participation of a large number of electrons. You see, we usually expect the outer valence electrons of an atom to be involved in bonding, and that's correct. But in the case of transition elements, what is the outer electronic configuration? It is n-1d, 1 to 10, and ns, 1 to 2, right? Now the energy difference between the ns electrons and the n-1d electrons is quite low. And that is why electrons from the n-1d subshell also participate in metallic bonding along with the ns electrons. Since these elements form metallic bonding, greater the number of unpaired electrons, stronger is their interatomic interaction and stronger is the metallic bonding. As a result, we need to provide more energy to break their lattice structure. And this is why transition metals have high melting points in general. The melting point reaches a maximum at the middle of each series. Now the maxima at the middle of these series indicate that one unpaired electron per d orbital is especially favorable for strong interatomic interaction. Thus, greater the number of valence electrons, better or stronger is the metallic bonding. Now the only exception in the 3D series is that of manganese. Despite having a D5 configuration, manganese has an unexpectedly low melting point. Now the other exceptions in the D block are zinc, cadmium, and mercury. All of these D block elements have much lower melting point than the others. And this atypical behavior is because they have completely filled D subshell. They do not have any unpaired d electrons that would increase or maximize their interatomic interaction. Now, as we go from 3D series to 4D series to 5D series, the melting point increases in the subsequent series. That is, melting point of 4D is greater than that of 3D and 5D is greater than that of 4D. This is because down the series, we have more number of electrons, which means stronger interatomic interaction. And overall, if you see, the melting point trend would be exactly same as that we observed in the 3D series. That is, it increases to a maximum till D5 and then decreases as we go towards the end of the series. Now, another consequence of more number of d electrons is the greater enthalpies of atomization. This is because, as we mentioned in the case of melting point, more number of d electrons or more number of unpaired electrons or valence electrons results in stronger metallic bonding. As a result, the enthalpies of atomization increases. Just as we observed in the case of melting point, the second and third series transition metals have greater enthalpies of atomization than the first series. That is, 5D series has the highest values of atomization, whereas the 3D series has the lowest values of atomization enthalpies. Let's now talk about the atomic size. In general, atomic radius decreases as we move across the period with increase in nuclear charge. And in the case of d block elements, the radii decrease from left to right. However, as we reach towards the end of the series, the size actually increases. Now, in the d block elements, there are two interplaying factors. One is the shielding effect of the d orbitals, which as we know is not very high because d orbitals do have poor shielding effect. And second thing is the nuclear attraction or the nuclear charge. As the d electrons have poor shielding effect, the outer electrons experience greater nuclear attraction, and as a result, the ionic radius decreases. Now within the series, you will see slight variation. For example, the ionic radii decreases steadily from scandium to manganese, but cobalt, iron and nickel have very similar ionic radii and the radius increases towards the end of the series. However, this variation within the series is quite small and can be broadly attributed to the slight increase in the shielding effect with the number of d electrons. With more number of d electrons, the shielding effect is expected to be slightly better, and as a result, copper and zinc have a slight increase in their ionic radius. Now, on comparing the 3D series with 4D and 5D series, we once again notice an increase in radius from 3D to 4D series. That is, 4D series elements have greater atomic radii as compared to the 3D series elements. However, no change in radius is observed between 4D and 5D series. So, what do you think is happening here? So, as we go towards the heavier elements and if you look at the electronic configurations of the 5D series, we can see that the 4f orbitals fill before the 5D orbitals. Now, this filling of the 4f orbitals before the 5D orbitals results in a decrease in the atomic radius, and this is called lanthanide contraction. As a result of the lanthanide contraction, the second and the third series, that is the 4D and the 5D series, have similar radii and also exhibit similar physical and chemical properties. The lanthanide contraction is caused by the imperfect shielding of the 4f electrons. So, as we go down the group, we can see that the atomic radius more or less remains the same, but the atomic mass increases, right? We know that the mass increases as we go down the group. So, as we go down the group, the atomic size decreases, that is, the size would be lesser than what is expected, but the atomic mass increases. So, what do we have here? Well, mass divided by size or volume is nothing but density. So, the decrease in atomic size or the metallic radius coupled with an increasing atomic mass results in an increase in the density of these elements.